Oh, hello. Welcome to part 4 of Perms, Combs, and Binomial Theorem. We're looking today at combinations. With combinations, we're looking at grabbing just a group of objects and not really caring about the order. With permutations, order mattered. But in combinations, order does not. With permutations, we knew that if we had to select our objects out of n, that's how we did it. That was the formula for a permutation. But if the order doesn't matter, and there are that many ways to order our objects, then similar to with our Mississippi theorem, with changing the order and it not mattering, we can say that if order doesn't matter, then we can take this amount that we had and also divide it by the different number of arrangements. Because all those arrangements are the same to us, they don't matter, that's what we get. That's a combination. That's the formula we see over here. If you're choosing r objects out of n, then there is n factorial divided by r factorial, n minus r factorial ways to do that. So whenever you're given a case on an assessment, on an exam, it's not really going to say that you have to use one or the other. And you do have to ask yourself, does order matter here? That's the key thing between distinguishing between permutations and combinations. So hereabouts, you've got 7 toys. Oh no, your parents say you have to give 3 away. How many ways are there to choose 3 toys to give away? Now, of course, we know that we're working with combinations today, so it's probably an NCR. But just asking ourselves, does it matter the order that we choose the toys to give away? If I choose my Lego spaceship and then my Lego pirate ship and then my Lego castle, is that different from choosing my Lego castle than my Lego spaceship and then my Lego pirate ship? No, because they're all getting given away regardless. So 3 are getting given away. How many ways are there to choose those 3? Out of these 7 toys, we're going to choose 3. I know the C stands for combination. I like to say it stands for choose. And calculator-wise, you're going to hit the 7. You're going to hit the NCR button. And then you're going to press 3. And then you're going to say equals. And getting a value out of that, I get 35. So there are 35 different combos of 3 toys out of those 7. Ooh, this one looks similar. You have 7 toys, you have to give 3 away. How many ways are there to choose 4 toys to keep? Okay. So out of 7 toys, we're going to choose 4 to keep. Punching that into your calculator, you get a value. I happen to get 35. Huh. That's a weird coincidence. That choosing 3 to give away is the same as choosing 4 to keep. Weird. There are more examples going on here. I dare you to give them a try and see what happens. I'm just going to keep going. You do your thing where you can pause video and all that jazz. Blah, 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 blah. Here we go. 6 numbers drawn out of 49. How many tickets would I have to purchase to guarantee winning the jackpot? So how many possible combinations are there? Because if only one is the jackpot, then you need to get every single ticket to win that jackpot. Out of 49, is that even a 9? Out of 49 possible numbers, we are choosing 6. For me, that gives a value of So it's possible that if the lottery is worth $14 million, you can make a slight profit. Possible. They do pay out for other smaller wins too, so don't hedge your bets on it. Oh, I have 15 grade 12 pre-calculus students. Ooh, and 4 are going to be my favorites. Randomly. Interesting. How many ways are there to do this? All right. Out of 15, I'm going to choose 4. And calculator again, because I'm not doing this by hand. But on my calculator, I'm getting 1365. Ooh, out of these 15 students, 5 are in AP Calc. I guess the rest aren't. And I want to select 4 favorites, but at least one's in AP Calc and at least one must not be in AP Calc. Interesting. There's a couple ways to do this. One option is to go through all the possibilities. You could say you have 1 AP and 3 not, and see how many ways. Or you could say that there are 2 AP and 2 not, and see how many ways. Or 3 AP and 1 not, and see how many ways. And then add all those together, get a result. That's not my personal preference. This isn't the worst. It's only like 3 calculations to do. But there is also another way. If all are AP, then I'm only choosing from a pool of 5 students. And I'm still choosing just 4 of them. And as it turns out, there are 5 ways to do that. If none of them are AP, so I'm going from the non-AP group, then I'm choosing from a pool of 10 students, and there are 4 students that I'm choosing. And when I take that, I get 210. Ow. Now there are 1,365 ways to select students in total. If I take out all the options that are all AP and take out all the options that have none with AP, then the remaining groups must have at least one of each category. So all the possibilities, I'll get rid of the ones that are all AP, and I'll get rid of all the ones that have no AP. Shabam. If you do want to try the other way, then to select 1 AP student and 3 who aren't, you're going to select 1 out of 5 students, and then by fundamental accounting principle, we're going to multiply that by the number of ways to choose 3 students out of the remaining 10. And we'll get a value there. And you'll operate similarly here. And operate similarly here. And we'll get those 3 values, add them up. Should get the exact same thing. Oh, the Athide Fam Jam wants to go for a walk, but oh no, there's 12. Groups can't gather in more than 10 at the time of recording this video anyways. Hello, it's Saturday, May 2nd, 1:55 p.m. So they're going to split into 2 groups of 6. There have to be 2 children in each group. This is a minor doozy of a case. Like, it's kind of a doozy. It's interesting. And they aren't all in the same household. That's why they've just split into groups. Otherwise, same household, then yeah, you can go groups out of 12. That's no problem. But anyways, there have to be 2 children in each group. So here's group 1. Here's group 2. And in group 1, I need to choose 2 kids. And I need to choose 4 adults. How many adults are there total? 8. So out of 8, I'm choosing 4. And then everyone else will be in group 2. That gives me a number. But that's no different from having to choose who's in group 2 first. Really. And then saying everyone else is in group 1. These two cases are the same. So when we take 4 choose 2 times 8 choose 4, we're actually going to divide that by 2 because the order of the groups themselves doesn't matter. Whether Orlando goes into group 1 or 2 doesn't make a difference if that group format is exactly the same. If that group is Orlando and Jennifer and Melanie and Chad and Kira and Desiree, whether the group 1 or group 2 doesn't matter. It's still the same group. Occurs to me, I never actually calculated this myself. Now I'm curious. So, oops. So 4 choose 2, and we're going to multiply that by 8, choose 4, and we're going to divide that by 2. I'm getting 210 ways. My goodness. Isn't that cray? And then this last bunch of examples has to do with something known as a deck of cards. Deck of cards has 52 cards, 13 of each suit, spades, hearts, diamonds, and clubs. And the values are 2, 3, 4, 5, 6, 7, 8, 9, 10. Then it's Jack, Queen, King, and Ace. So there's 13 values of each suit, just in case you've never seen a deck of cards before. I know a lot of people have, but you never know. That's what's involved in a deck of cards. And apparently the whole point of teaching this unit is to teach you how to gamble. So let's learn to play poker. How many 5-card hands are possible? So you dealt 5 cards out of 52. Doesn't matter what order you get them in, you can still get all those cards. And here I get this. But how many 5-card hands contain only the suit of spades? So I'm still going to choose 5 cards, but I'm only choosing them out of 13 because there's 13 spades. And there I get 1287. How many 5-card hands contain a flush? So all cards are of the same suit. That means you could have that all the cards are spades, or all the cards are hearts, or all the cards are diamonds. I forgot the spelling. Or all the cards are clubs. We know that if they're all spades, that's 1287, because there's 13 spades. We chose 5, gave us 1287. But the same follows for all hearts. The same follows for all diamonds. The same follows for all clubs. And those are completely independent. There's no overlap. There's no chance of you getting both all spades and all hearts. There's no commonality between the two. So we can just add all these together. And the total is that. How many 5-card hands contain at least one queen? Again, multiple ways to do this. You could check how many have one queen, exactly one queen, and how many have 2 queens, and how many have 3 queens, and how many have 4 queens, and then add all those together, get a result. Personally, I'd start by checking how many have no queens. So if there are no queens, then while I'm still choosing 5 cards, I'm only choosing them out of 48. There's 52 cards total. There are 4 queens. So if I remove those from the pool of possibilities, I'm only choosing from 48 cards. In which case, that's how many cards, or how many 5-card hands there are that have no queens. So then up here, I'm not worrying about this being 1 queen or 2 queen or 3 queens or 4 queens. I'm just taking the total hands and subtracting the hands with no queens. Which was that number up there. And getting rid of the number that have no queens. Neat. And how many 5-card hands contain contain at least 2 queens? There's a couple ways to do this. I don't really have a preference here. You could take the number. What do we have? We have the amount that have at least 1 queen. This is how many hands contain at least 1 queen. If we take away all the hands that have exactly 1 queen, then we'd have the number with 2 queens. At least 2 queens. Alternately, find out how many have exactly 2. Find out exactly 3. Or how many have exactly 4. So, to show you how to do this, if there are exactly 2 queens, then from the 4 queens, we're going to choose 2. And it's a 5-card hand, so we still need to choose 3 more cards. And we're going to choose those from the remaining 48. If we want exactly 3 queens, then from the 4 queens, we're going to choose 3 of them for our hand. And from the remaining 48 cards that aren't queens, we're going to choose 2 cards. And if we want exactly 4 queens, they're going to choose all 4 queens. And from the remaining 48 cards, we need 1 more. Each of those gives us a value. Here again, we add because they are completely separate events. You can't have exactly 2 queens and exactly 3 queens at the same time. So we just add them all together, and I get that. So just remember that you do have to read carefully to determine whether a problem requires perms or coms, or neither to solve. Like, it could just be regular, straight up fundamental counting principle. How many options for this first slot and second slot, etc. But the key is that order does not matter for combinations, whereas for permutations it does. The textbook practice work is probably all combinations, but still make sure you're reading the problems carefully. They might not always be as direct as they seem. It's very easy to rush through and just say, yes, I know exactly what it is, but accidentally discount possibilities. For example, some people might look at this at least 2 queens and say, all right, I'll select 2 queens, and then out of 50 cards, I'll select 3 more, because I've got 2 cards done. There's 50 to choose from. That way I get at least 2 queens. Maybe I get more queens here, maybe I don't, who knows. But that does kind of cause an overlap in possibilities. I hope that didn't confuse you further. In any case, practice the practicey work. Let me know if you have questions or comments or concerns as you do so. And as always, believe in yourselves, believe in the dream. Peace out, goodbye.